Ready to get started with regression analysis? Good, good. All right, regression analysis I think is really exciting because it's an interesting topic to begin with, and also it's something that you'll use as an MBA student, you'll use as a business professional. You'll hear constant studies about how we regressed one variable against another. Now you'll be able to understand more about what that means and how to evaluate studies, and it's just very useful. The other reason I'm excited about this is where some of your hard work from previously in the quarter will pay off. I've made you learn various things, and these things are going to crystallize somewhat, I hope, with regression analysis, because regression analysis draws on a variety of things. So let's do it. Let's do regression analysis. So regression analysis is how two variables correlate with each other. So for example, if interest rates go up, the stock market, what happens to the stock market? It goes down, right? Okay, so those are negatively correlated. So higher interest rates would mean lower stock market. What else? Higher temperature would mean more ice cream sales, perhaps. More money spent on advertising might mean more revenue. There's a correlation there, and you might want to figure out what is the correlation there. How much are we actually getting an increase in terms of revenue for each dollar we spend in advertising? What else? What are some other variables that are correlated with each other? Yes, okay, so more education would mean more income. In general, we might be able to figure out an actual equation that would say for every additional year of education, you would be expected to earn $7,200 and whatever dollars. Good. Anything else? All right. So we'll learn not only is there a correlation, not only how to talk about whether or not we believe there truly is a correlation, but exactly what I just did, mathematically quantify it. For every 1 year increase in education, we would expect a certain amount of income to increase. So let's look at this example. Here I'm talking about correlating two variables. One is the number of hours you spend studying, and the other is your grade in your statistics class. I have a sample of 6 students where I noted their statistics grade and the hours they spent studying. So let's look at a couple of these. Tell me the difference between these two students. All right, student A versus student B. What do you know about those two students?
A studies less.
A studies less, yes.
And B studies more hours, therefore. The more hours you put in, the higher your grade.
Yeah, okay. We may not be ready to quite say that, but we know A studies less and got a low grade, and we know that B studied a lot and got a high grade. Okay, and we're gonna see if we can build a case. Is there a correlation between these two variables? How about these two? Person A, person B here. What do you know about those two people? They got the same grade, right? Okay. What else? They got the same grade. What was different about them? Yeah, one studied less. Okay, so in this case, we're not sure. Is the correlation significant there? All right, so let's decide if we can draw a line of best fit that would fit these sample data to the best extent possible and allow us to mathematically say for each additional hour of study or unit of study, your grade is expected to increase by a certain amount. So we find a line of best fit, and we say that is our regression equation. So that line can be quantified with algebra. you'll see a y equals the intercept plus the slope times the x variable. Maybe you remember from high school algebra, y equals mx plus b, you have the slope, you have the intercept, right? That's quantified that way. So the input is the hours of study, and then the output, the y variable, is going to be the statistics grade. So based on this line, you will go to someone besides one of these 6 students, and you'll say, hey, how much time did you spend studying in statistics class? And they'll tell you, right, because they wrote it down or whatever. They'll tell you, I spent exactly this much time studying. And you'll say, I bet you got a grade of such and such. And what will they say to you? How did you know that? How did you guess perfectly what I got? And you'll say, because I ran a regression and I determined that that was the regression equation. Now, when we talk about whether or not we have a good regression equation, all right, with this line, do we consider it a good model? Well, it doesn't hit the points exactly, so there's a question of how close it is to the data points. So the first thing we'll look at is what we'll call performance measures, which are essentially that. How close are the dots to the line? If they're really close, then we have a good model that we can rely on. We can use that model to predict things. We would invest based on that model. We think we could sell a lot of product because of that model. If the lines are really far apart, we're less confident about what we're able to predict. So in quantifying how well this line fits the sample data, we would first say, how much of the deviation does it explain? Or how much of the variation does it explain? And when we talk about variation, we'll say variation from the average. So with these 6 sample data points, we would say, what is the average grade of these 6 students? And so the average grade is right here. It's just a mathematical, what was the average grade? It was C+. That was the average grade. And then we look and we say, well, guess what? This student right here is above average. And the way we'll pose the question is we'll say, what would explain that variation from the average? Do we have something that we've talked about that would explain why this student has so much variation from the average?
Yes,
Yes, what is it?
that student studied more hours.
Exactly, exactly. I'm not trying to trick anybody, but that's just the way we look at it. To what extent are we able to explain the variation from the average? Well, we have something that we think is correlated with statistics grade, and it's hours of study. All right. So, we're going to go over some basics about linear regression. We'll talk about performance measures, which is how well does that line of best fit the sample data. The second thing we'll talk about is the inference side of regression analysis. Remember, I've talked about inferential statistics, and I told you not to be scared by that term because it just means what? What does inferential statistics mean?
Educated guess.
What's that?
Educated guess.
You don't have all the information.
Making a conclusion from the analysis.
You're making a conclusion, okay, very good. You're making a conclusion about what from what? I'll give you a hint. That's a fill in the blanks. One of the answers is the sample, the other is the population.
Population based upon the sample.
Exactly. All right, you're making a conclusion about the population based on the sample. So based on this sample, what can we infer about the whole population? Because this sample is just 6 students. Okay, so, you know, is 6 students enough to infer something about the whole population? Well, we'll use math, we'll use confidence intervals, we'll use things we've studied all quarter to make that decision. Okay, so inferential side of statistics, what can we infer about the whole population? Estimating the intercept and slope terms for the population regression line. Okay, so this is the slope for the sample data, and we want to know how close that is to the slope if we had all students who have ever taken a statistics class on this graph. That would be the population regression line. Key hypothesis test in simple regression. So the key hypothesis test is, do we have a slope that is different from 0? So if we had a slope that was 0, what would that mean? Like if this were, let's say, alright, this is an upward sloping line. What would a slope of 0 look like?
Straight line.
Straight line, exactly. A slope of 0 would be a straight line. What would that mean about the correlation between study and statistics grade?
There is none.
There is none. There's no correlation. It is a flat line. It doesn't matter how many hours you study, that gives us no predictive, no explanatory ability in terms of what your grade is. Now there are other things that determine your grade, but as far as we know, study time does not determine your grade. So the key question we'll ask is this slope 0? Is it so different from 0 that we can say conclusively we think there is a positive or negative correlation? And so that's going to be our key hypothesis test. The null hypothesis will be, in the full population, the slope is 0. Null hypothesis. And then we will say, do we have overwhelming evidence to prove that that is not true? And if we do, we will reject that the slope is 0, and we will conclude that we do in fact have a positive or negative slope. That will be our key hypothesis test. And then we'll look at a printout from Excel. It's just a printout that you would get if you were to run some Excel data on two variables, see if they're correlated. You'll be able to understand pretty much everything that Excel that will be on that printout. Okay, so some basics. Regression analysis attempts to identify a mathematical function, a slope, line of slope, that relates two or more variables so the value of one variable can be predicted from the value of the other variables. So you tell me how much time you spend studying, I'm going to try to predict what your statistics grade is. We will have, in simple linear regression, one dependent variable and one independent variable. I think of it this way. The independent variable is what you put into the model. In our example, that is hours of study. So you go and you ask someone, how many hours did you spend studying? You put that into your model. The dependent variable depends on the independent variable. So what is your statistics grade? Well, it depends on how many hours you spent studying. So in our example, the independent variable is hours spent studying. The dependent variable is your statistics grade. And we'll look at it, the independent variable is on the x-axis, the horizontal axis. The dependent variable is on the y-axis. So you're going to tell me x, and I'm going to predict y. Independent variable, you tell me, and I will predict the dependent variable. Next week we will look at multiple regression, which is two or more. No problem. Next week we'll look at multiple regression, which is two or more independent variables. So our one independent variable right now is study time. What could be some other independent variables which would predict that dependent variable of your statistics grade? Just think of some examples. Shout them out. Anyone have one?
Can you repeat the question? Something that would what? Influence the grade?
Yes, something that would influence our dependent variable of your statistics grade. What would be an independent variable besides the hours you spend studying? Participation. Okay, are you just studying, by yourself, or are you actually participating in class, asking questions? Explain. Remember, I always say explain to your neighbor.
Yeah.
All right, so amount of participation. Adamas.
I believe that the person could have bigger experience or probably
Smart.
Yes. Years of experience in statistics, IQ, participation, what else? Attendance, whether you came to class. Great. Interest, whether or not you care.
Yeah.
Good, okay. Alright, well, I didn't get a good grade because I didn't care. I didn't like how much you liked the professor, okay? I did, you know, if you didn't like the professor, then you didn't want to do the work, you didn't want to come to class. Okay, so those could be independent variables in a multiple regression that would explain one dependent variable, statistics grade. We'll look at linear, straight line. We'll look at straight line relationships. We don't want to do anything more complicated than that yet. That's it for that slide. Okay, so let's review a little algebra of a line. So I have a line that looks like this. I can write an equation for that line. I can use another chair. Do you need a chair?
Yes.
All right. Well, great capacity.
How is that
Where should I put it? Should we put it? Where should we put it? All right. Don't everybody jump up to volunteer at once. Right here. Right here. Right here. Okay. Perfect.
Thank you.
All right. So I have a line, and there's an equation for that line. Y equals the intercept. You may have seen that called something different when you studied high school algebra, but now we're going to call it the intercept with small a, plus b. B is going to represent our slope, and x is going to be the independent variable. So we're going to input x into this model. We're going to multiply it by the slope and add it to the intercept, and we're going to calculate these two terms. Based on the sample data we have of our 6 students, we're going to find what these two terms are based on that line of best fit, and then we're going to predict your grade. So this is what our model is going to look like. We're going to input hours of study, and we're going to spit out your statistics grade. So we care about the intercept because that's important for math, but the thing we'll talk the most about is this slope. We want to know for a 1 unit change in the independent variable, how much can we expect the dependent variable to change? So for a 1 unit change in study time, how much would we expect our grade to change? So slope, you may remember, rise over run. So we have 1 unit on the run, b is our rise. So can you just give me a ballpark figure? What do you think the slope is for this line?
One.
Slope, yeah.
0.5.
All right, we got 0.5, we got 1, 7. All right, it's the rise, so for a 1 unit change in x, how much change would we expect in y? So it's about 0.5. So for 1 unit change in hours of study, we would expect your grade to change about 0.5. And that's the key thing that we'll be interested in. What is the slope of this regression equation? The intercept is just the math to make everything work out. And ultimately, when we look at just the intercept, it won't make too much sense if we look at it theoretically. Because you might say, well, what if we spend 0 hours of studying? Well, then we would expect a grade of this much, which may or may not make sense. For this one, it kind of makes sense. But there's a lot of models where it just doesn't make sense. So we calculate the intercept, but we focus our attention mostly on the slope. Okay, so simple linear regression, 1 independent, 1 dependent variable, produces a straight line, indicates to what extent variables are associated. It does not by itself prove cause and effect. So just looking at that regression equation, if we decided we were confident in that regression equation, we could not right off the bat say more study time causes a higher grade. We could just say that those two variables are related. Now we would probably try to make a case for that it does cause a higher grade, and we would just have to think that through. We have to say, well, is there anything we're missing? Is there something else, a third variable, that could actually be influencing both? Like a third variable that might make you study more, and may make you spend more time studying, and might make you have a higher grade. I don't know exactly what that variable would be at this point, but you would just think that through. So when you see that there's a strong linear relationship, you don't want to jump right away to that's causation. You want to be careful and think that through. Because statisticians will sometimes point out that correlation does not necessarily mean causation. Have you heard that before? Alright, so it's an easy little line to memorize. You can use it to annoy people who've done a lot of work. Alright, but you don't want to be the person who's annoyed by it. You want to say, I've thought of that, I see there's a correlation, and then I've thought just intuitively whether or not we can make a case for causation. Alright, we use a scatter diagram. We have independent variables on the x-axis. We have dependent variables on the y-axis, and we plot them based on those inputs. Fitting the line, generally the line will not fit the data perfectly, so we want to find the best fitting line. So how do we find the line of best fit? Well, what we do is we find the line that has the smallest distance from each of these points. So, looking at this line, what we could do is we just measure the distance, add them all up, and say the total distance from the line for each of these points is such and such, is 7. Right? Could we do anything to this line to make that distance smaller? To make it 6.7, 6.8? Right? Could we tilt it a little bit? Could we move it down? If the answer to that is yes, then we would do that until we get the smallest difference. That's our line of best fit. Now, statisticians, instead of just measuring the actual distance, they like measuring the distance and squaring it. That has a couple advantages. One, we don't get confused between positive and negatives. Right? This might be a positive difference, this might be a negative difference. So we just square it. We add them all together, and we find the line of best fit that makes the sum of squared deviations as small as possible. So the sum of squared differences is what we want to be as small as possible. Least squares criteria identifies the best fitting line as the line that minimizes the sum of squared vertical distances of points from the line. So y is going to be our regression equation, our predicted value for y. Y with the triangle hat. Wait a minute. Y is going to be the actual, y is going to be the actual outcome. Y triangle hat is going to be the predicted value for y. We're going to take that difference, square it, add them all together. Whatever we can do, however we can tilt that line to make that the smallest, that is our line of best fit. Now, there is a formula for that, and I'm just going to show it to you. I'm not going to make you calculate it, but I'm just going to show it to you because I found it surprising that we could figure it out if we wanted to. When I first studied this, I thought, oh, that's just something statisticians would do, Excel does, there's no way anyone would possibly do it, but it turns out that there's actually an equation for it. And the problems in your textbook actually ask you to figure these out. They ask you to figure out what is the slope of the line of best fit and what is the y-intercept for the line of best fit. And surprisingly, it's not that hard. When I first taught this class a few years ago, I did those early problems and I figured it out, like without Excel, with just a calculator. You know, N is the total number of your sample. We had 6 samples. For each, you multiply the hours of study times the grade, add those all up, minus the sum of the hours of study times the sum of the grade. And you do all of that stuff carefully and slowly, and you will come up with the slope for the line of best fit. And then you continue, y with the bar over it is average y and times the slope times the average x, which will give you the y-intercept for the line of best fit. So, we could do this if we wanted to. We won't. We'll just input the data in Excel, and Excel will spit out the slope and the intercept for the line of best fit. And then we'll have it. We will have our regression equation. We will have a predicted value for y based on number of hours studied, based on some independent variable. So we will calculate this A and B based on either doing it ourselves or putting it in Excel. And then we'll go and we'll ask someone. We'll say, hey, how many hours did you spend studying? That's the X. And then it will tell us what their expected grade is. We'll tell them what we think their grade was, and they'll be shocked that we got so close. Estimated regression equation. So now, once we have created that equation, so this is going to be some number, we want to think about how well that line fits the data points. We call these performance measures. Are the data points really close to the line, or are they really far away from the line? If they're really far away from the line, we don't like the model as much. If they're really close to the line, we're like, yeah, we really have something that explains things. And the way we're going to quantify performance measures is we're going to look at the differences in the amount of variation that we're able to explain versus the amount of variation that we're not able to explain. We're going to look at that in relationship to the total variation we see. So these 3 things, explained variation, unexplained variation, and total variation, they will be our building blocks for our performance measures. And then we'll use some math to calculate 3 different terms: the coefficient of determination, correlation coefficient, and standard error of the estimate. So I'll explain these 3, and then I'll just show you the math of how we get these 3. Alright, so feel free to slow me down, ask questions if you have them. Tonight's class, there's really no exercises in the middle. All the exercises are at the end. So stop me, slow me down if we need to interact a little bit, ask some questions. Alright, so I mentioned when we talk about variation, it's variation from the average. So this y with the straight bar over its head, that is the average statistics grade. This particular student deviates significantly from the average. What would explain why this student deviates significantly from the average?
They studied longer.
Study more, study longer. That explains some of the variation. See this whole thing here? That's the total variation. The fact that this student studied a lot explains some of that variation. So we used those formulas and we calculated this regression equation. Y equals the y-intercept plus the slope times x. And this is what that line looks like. So we are now able to explain some of that variation. So the total variation is from the average to the actual data point. And we're able to explain some of it, but not all of it. So the total is from here. From here, from the average to the regression line, we're able to explain that. We're able to say, well, we would expect that student to have a higher grade because look, that student spent this much time studying. But what does that leave up top here? Unexplained variation. So we think we know why the student got a grade this high, but we don't really know why the student actually got a grade this high. Well, other factors that we mentioned before. That student had a statistics undergrad, that student was interested in the class, that student didn't have a full-time job. There were other things that explained that variation, but as far as this model is concerned, that variation is unexplained. So, we're going to quantify the unexplained, the explained, and the total variation. And if we say we have a very large amount of explained and a small amount of unexplained, we're going to be happy about that. And we're going to say this model is a good model, a strong model that we can rely on. Now we calculate explained, unexplained, and total the same way we calculate that line of best fit. We add up the total, the unexplained variation here. We don't care so much if it's positive or negative, so we square it. We do that for each of the 6 data points, and we add them all together. So this unexplained variation is the squared unexplained summed up for all data points. Same thing for the explained variation. We say, how big is this? All right, that's the explained variation. We don't care if it's positive or negative, so let's square it. And let's do that 6 times, add the total squared explained variation, and that's going to give us our sum of squares regression, we'll call it. Sum of squares of the explained variation is our sum of squares regression. We'll call it SSR. There'll be a slide on it in a minute. So sum of squares regression. The total unexplained variations, squared and summed for each data point, will be our sum of squares error. And then the total variation, for each of these data points, we'll take this number, this distance, we'll square it. We'll do that 6 times. That'll be our sum of squares total. And I'll stay here for a minute. I'm going to go to the next slides, but I'll come back to here just to make sure that doesn't confuse you.
Question.
Yes?
Regression is unexplained or explained?
Sum of squares regression is explained variation. So think of it, what does the regression line explain? So sum of squares error is the unexplained variation. Sum of squares regression is the explained variation. Sum of squares total is the total variation. All right, if you're feeling good on those 3 points, you've got the building blocks we need for the next step. If you're not, let's just stay on this slide for a minute and make sure that you are. Try to take a brief pause. All right, so to sum up, we looked at this particular student. And we said this student varies significantly from the average statistics grade. The total variation is from here to here. Let's calculate the sum of squares total variation. So let's square that and do that for all 6 data points. Sum of squares total. Now some of that total variation can be explained. Explained why? With our regression equation, which uses hours of study as an independent variable. So for each data point, let's measure the amount we can explain, square it, add it all together, sum of squares regression. Some of that variation cannot be explained. Let's measure it for this data point, square it, do that 6 times, add it all together, sum of squares error. Okay, good there? All right, so then the 3 performance measures just look at the relationship between explained and unexplained. The first one is called the coefficient of determination. also called R squared. This is the percentage of the variation that can be explained. It is mathematically the explained variation divided by the total variation. What is our explained variation? Sum of squares regression. What is our total variation? Sum of squares total. So the coefficient of determination, also called R squared, it's a number between 0 and 1, right? Because total variation is 100% of the variation, and explained is a certain percentage of that. So it's between 0 and 1. Also, you could say it's between 0% and 100%, same thing. And that percentage is the percentage of variation that is explained with your regression model. So if I tell you the coefficient of determination is 92%, would that sound impressive to you? Yeah, I can predict 92% of the variation just based on one independent variable. So you just need to tell me one data point and I can pretty much quantify with 92% accuracy what the dependent variable will be. On the other hand, if I told you I have a regression equation that has an R squared of 22%, you would probably be less impressed. Like, oh, 22% of the variation, that's just maybe even random chance that you're able to explain that much. There's probably some third variable you're not even considering that really explains the variation. So, coefficient of determination, also called R squared, that is the percentage of variation that can be explained by your model. The next performance measure is called the correlation coefficient. This is simply the square root of R squared. So R squared, if you remember, is the sum of squares regression divided by the sum of squares total. So these are squares. These are squared units. So let's get them back to units that resemble what they originally were by taking the square root of that. Look at that logic. The more interesting thing about the correlation coefficient is we will make it positive or negative. So it will be between -1 and 1. So we'll take the square root of R squared, and then what we'll do is we'll look at the regression line, and we'll say, is it sloping down? In which case, the correlation coefficient is negative. Is it sloping up? The correlation coefficient is positive. So our example we're looking at right now probably has a positive correlation. So more study time means more grades, better grades, higher grades. I give an example at the beginning. Higher interest rates would mean what for market performance? Lower market performance or higher market performance? Lower. So higher interest rates, lower market performance. That is a negative relationship. So the correlation coefficient for that regression would be negative. The other exciting thing about the correlation coefficient, if you study finance, has anyone studied that term beta?
Oh, I heard about it a lot of times, stock market and stuff.
Yeah, it's essentially the relationship between an individual stock and the whole stock market. And the correlation coefficient is the key input in calculating beta. So you'll start with the correlation coefficient, which will be between -1 and 1, and then you'll add something to that. You'll scale the standard deviations of the individual stock in the stock market. But the correlation coefficient is the starting point for beta, the starting point for that topic in finance. Okay, so correlation coefficient is the square root of R squared. It can be, the exciting thing about it is it can be between -1 and 1, and it can tell us if there's a positive or negative relationship. Last performance measure is the standard error of the estimate. This is the standard deviation like metric for regression analysis. Standard error of the estimate is, on average, how far away are the data points from the regression line? So if I were to look at these two models, this is model A, this is model A, this is model B. Now both of these have the same average grade and the same slope to the regression line, but they're different. Model A, model B. What's the difference between model A and model B? Model A,
And model B, the distance is further.
model B, the distance is further. Alright, so which regression equation would we have more confidence in? A
A.
or B? Exactly. A we would have more confidence in because the standard deviation, called the standard error of the estimate, is bigger in model B. Standard error of the estimate, on average, how far away is each data point from the regression line? Now, we already looked at how far away each data point is from the data line with this sum of squares error. This is unexplained variation, but it's squared. So we want to do a couple things before we can say we have an average distance of each data point from the data line. First, we divide by roughly the total number of data points. And then since this is squared, we take the square root of it. So if the squared came out to 16, we would take the square root and that would be 4. 4 would be the average distance of each data point from the data from the regression line. So sum of squares error, divide roughly by the number of data points, and then take the square root of that. Now, we don't divide exactly by the number of data points. We divide actually by number of data points minus 2. So when we divide by a smaller number, what happens to this standard error of the estimate? Does it get bigger or smaller? We divide by a smaller number, does it make the end result bigger or smaller? Bigger. Okay, so we divide by a smaller number, it's going to make the end result bigger. Okay, so this is the same logic as when we started using the t-distribution, and we said, well, we're calculating our own sample standard deviation, so we're going to divide by n minus 1, and then so the standard error is going to be bigger. Same thing here. We have more unknown variables. We have an unknown variable of the intercept and the slope. So to account for those unknown variables, we're going to divide by a smaller number, and we're going to make our standard deviation-like term, a standard error of the estimate, a little bit bigger. More unknown variables, we'll call our standard deviation bigger, just a little safety margin when we make our conclusions. The burden of proof becomes a little bit higher if we're trying to prove we have something statistically significant because of those unknown variables. All right. So we've got 3 performance measures. We created a regression line based on some 6 points of data. We took 6 students. We asked them how much they studied and what grade they got. We plotted that. We created a regression line. We calculated how much of that variation we calculated the total variation for each of those 6 students. How much of that we could explain with our regression equation, how much of that was left unexplained, and we put that together for 3 performance measures. First one, all right, what's the first performance measure? Somebody just reiterate what this first performance measure is, coefficient of determination. What does that tell us?
Tell us on what you just described to us earlier, just now.
Yeah,
the
yeah,
S2,
yeah.
and what the SSR means and SST means. And then,
Yeah, okay. So what's SSR?
Regression.
regression, total.
Sum of squared regression,
Yeah, sum of squared.
also
regression.
known as explained variation,
And then the sum of squared total.
total variation. Alright, so we have the explained variation over the total variation. So how would you sum up what is the coefficient of determination to somebody else in your own words? What is the coefficient of determination?
Explain variation over total variation.
Explained yeah, okay, maybe take it, give me, that's not wrong, that's perfectly fine. Somebody else, give me some
The
other.
amount of variation in Y that's explained by
Yes, the amount of variation in y that is explained by x, and we could say specifically the percentage of variation. Give you an exact percentage of variation, 89%, 92%. I have a model that can explain 74% of the variation. Invest in my company. Coefficient of determination, the percentage of variation which can be explained by our regression equation. And I feel like there's something comforting in that. It tells you an exact percentage. The correlation coefficient, it's not, doesn't have that same exact nature to it. Speaking of correlation coefficient, what is that? How do we get it? And what is one thing we especially like about the correlation coefficient? How do we calculate it first of all? What's the correlation coefficient?
The coefficient of determination squared.
It is the square rooted.
The square root.
Exactly, Adonis.
So correlation, when I hear that word, it sounds like relation. Relation of what? And I was just thinking that it's probably between 2 points, so is that the slope of the equation, the relation?
It is not the slope. No, it is not the slope. We would need other things, yes, it's not the slope.
Is it close to the slope?
It,
It's trying to
Does it
find
involve
a
the
line,
slope?
a true line.
It does
of
involve the slope, doesn't it? Because it tells you if it's a negative or a positive.
If we try to
Yeah.
find the truth of it or something.
it tells you if the slope is negative or positive, but it doesn't tell you the slope. Yeah. So
Okay.
for our purposes, the correlation coefficient does not involve the slope. So the answer is no, it does not. The only reason, Adonis, I'm hesitating is because I told you about beta. So it kind of does there. Like it's the starting point for the slope, but then you need to add relative standard deviations of the company and the stock market. So it kind of does once you get to beta. For our purposes, it does not involve the slope except for what Amanda says. It just tells you if the slope is positive or negative, and that is what we really love about the correlation coefficient.
Okay,
And what would a negative slope mean, Thomas?
right. What a negative slope means, you want
Yeah.
to answer that?
Yes,
It's probably heading south.
It's a
negative.
yes.
It's negative.
It's negative, it's bad, right.
It's an inverse relationship.
It means there's an inverse relationship. Okay, so if temperature goes up, ice cream sales go
up. Up.
Yeah.
Oh, it's not go up.
yeah, so that's a positive relationship.
Right,
So temperature goes up, sales of long underwear
go down.
down. Alright, that's an inverse relationship. So you would not want to advertise your thermal long underwear in on the hottest day of the year. Okay, so correlation coefficient is the square root of r squared. And what we really love about it is it's positive or negative, tells us if there's an inverse relationship or a positive relationship. And last performance measure, what does standard error of the estimate tell us?
The standard deviation type measure, the measure.
How close the points are to the line.
This
How close the points are.
Yeah.
Yeah, how close the points are to the line on average. That's it, yeah. How close the points are on the average. Now why do we divide by this n minus 2?
Because if you divide by a small number, you get a larger result.
Yep, so it makes this standard error a little bit bigger. Why do we want to make it just a little bit bigger, Wendy? Or anyone else?
So you see our safety margin?
Yeah, to account for unknown factors, to give us a little bit extra cushion to our standard deviation. And it's going to make our burden of proof a little bit higher to account for the fact that we don't know as much as we would like to about this data. Great, great. You've got performance measures, right? How well does that line of best fit those points? Next question. What can we infer about the whole population? So, our data set of 6 students gave us a sample regression equation. We have a predicted value for y, predicted statistics grade equals a intercept plus slope times x. All right, now we want to infer something about the whole population. So this sample intercept, we want to know if we had every single statistics students ever, and we measured their grade and the hours they spent studying, what would the y-intercept be for the population line? And we're going to upgrade from lowercase a to the Greek letter A, alpha. That's going to be our population y-intercept. All right, and for our slope, the little b is our sample slope. We want to know if we had every single statistics student ever measure their grade, measure the hours they spend, what would the slope be for the whole population? So we go from lowercase b to Greek letter b. That must mean something bigger and better, right? Anytime you go to Greek letters, you've got something. So this is our population regression equation, and we just call this the estimated value for y equals intercept plus population slope times x. So here's the question. We have this. What do we think this is? We have this. What do we think this is? Now we've done something similar to this with confidence intervals. Remember we took a sample mean, and we said, well, what do I think this is if I were to measure the entire population? And we stood up and we said, I'm 95% confident that the true of this is between this interval and this interval. So do we have a tool? After we measure this sample slope, do we have a mechanism, a tool, something we've studied before, which would tell us the likelihood of this sample outcome, and how likely this sample outcome is, how close we could expect it to be to the true population slope? Do we have a tool like that? What's it called, Wendy?
It's something about
The likelihood-
sampling distribution and sample something.
Sample slope.
Yes, it is the sampling distribution of the sample slope.
Oh, there you
We've got it. Let's get right to the fun one. Sampling distribution of the sample slope. So this is a frequency distribution of every possible sample slope. So some poor graduate student sampled every single possible combination of samples and put it on this frequency distribution. It turns out this frequency distribution is normally distributed. The center of this frequency distribution is the true population slope. And because it's normally distributed, once we calculate the standard deviation of this frequency distribution, we can quantify how confident we are that our sample slope fell within a certain range of the true population slope. So within 2 standard deviations, 3 standard deviations, we can say exactly how confident we are that this sample slope would fall in that range. Same thing with the sample intercept. We have something we'll call the sampling distribution of the sample intercept, normally distributed. The center is the true population intercept. standard deviation can be calculated from the sample data. Okay, so let's look first at this. This S subscript A, that is the standard deviation of the sampling distribution and the sample intercept. Yes, ma'am?
Now I have a question. On the slide, and that it has an X, does that make a difference?
There's another one. If you
Is it
keep
another
going,
one?
yeah.
Which way? This way? Forward or backwards?
You said the X.
No, it's on slide, what is this? 28?
Okay. Oh, yeah. So this
So that's
is,
different, where does that one
this
come
is
from?
just our predicted value for Y. So how do statisticians say that? The expected value of Y given X, I wouldn't worry about it. It's just our predicted value for Y if we had every single point of data in the whole population. So we have this. Yeah, it's just our predicted value for Y. That's all it is.
Okay.
Right. So now that we've collected some sample data, we have this sample regression line. We know that this sample intercept falls on the sampling distribution of the sample intercept. And we know the standard deviation of the sampling distribution of the sample intercept, because I just showed you this formula. You could calculate it if you wanted to, but you'll just do it in Excel. Excel will spit this out for you, and it will give you your standard error. So you want a confidence interval for our Greek letter A. Alright, so our true population intercept is our sample intercept plus or minus some number of standard errors. How many standard errors? Well, it depends. Depends on how confident you want to be. If you want to be 99% confident, then certain number of standard errors, 95% confident, fewer standard errors. And we're going to use a t-distribution to determine the number of standard errors. Specifically, we're going to use a t-distribution with n minus 2 degrees of freedom. So, suppose for our sample, we wanted to be 95% confident. All right, we have a sample of 6. We want to be 95% confident. So we're 95% confident. What percentage of the time are we going to get it wrong? 5%. All right, sometimes we're going to get it wrong by being too high. Sometimes we're going to get it wrong by being too low. So we'd have 2.5% in the upper tail, 2.5% in the lower tail. So we would look on the t-distribution. Our sample size is 6. 6 minus 2 is 4. So that would be 4 degrees of freedom. And there would be 2.5% in either tail. Want to check that out for me? Sounds like at least one person is, so if you're not, don't worry. They'll get the answer. You just know you need to flip back to that t-distribution that you used a few weeks ago. 3.776? 2.776? Okay, so, alright, if you want to be 95% confident, you're going to take our sample intercept, whatever it came out to, plus or minus 2.776 times the standard error that you calculate. How are you going to calculate that standard error? You're going to use this formula. Excel's going to do it for you, one of those two. How is Excel able to do that for you? Because guess what? There's this thing called the sampling distribution of the sample intercepts, which has all those great properties which allow us to predict confidence intervals. Yes?